All right. Good afternoon, everyone. Welcome. Hopefully you're enjoying the nice temperatures for as long as they last. I don't know. It brings fond memories to me. I always, when it gets cold, it always makes me kind of happier because it just brings back. It's always a fun time of year. I don't know your experiences. Hopefully, you have good memories of it. Um, Today, we're going to get into conservation energy. We will get through most of this. We'll finish most of this today. There'll be a little bit that I'm going to do today, but we'll actually be able to start momentum a little bit sooner, which is good for us because momentum, we're getting back-to-back years and all that jazz. So, anywho, conservation of energy should be very straightforward for many of you. You've probably learned a lot of what I'm about to tell you, but we're going to derive things and calculate things, and a lot of y'all, this should be. If you've ever taken physics, this is like a classic. If you've taken physics in the past, conservation of energy is something you've done. It's really, really straightforward. Even if you haven't done it, it's very straightforward. Very, very straightforward. Every equation, every problem basically boils down to energy initial plus the work done equals energy final. It's great. Big fan of it. Okay, joke of the day. All right, two artists had an art contest. It ended in a draw. Two artists had an art contest. It ended in a draw. It's good. There you go. Tell your friends. All right. So let's jump into this. And the continued theme of energy is that everything is derived from the work equation. Every single thing I'm teaching you basically comes from work equals the integral of F dot dl. And you're going to see that today. We're going to derive potential energy for gravity from work equation. We're going to derive the equation for the energy through the spring from the work equation. We're going to derive conservation of energy from the work equation. Everything is derived from the work equation. So basically this entire last 2 weeks is just the work equation and finding equations from it, which is kind of cool. We'll talk about potential energy. We'll talk about the relationship between potential energy and work and conservation energy. And it's really, really straightforward. In my opinion, this is one of the most straightforward things I teach you the entire semester. So hopefully that's like a good thing. Hopefully it goes really smoothly for you. All the problems are basically done the same way, which is nice. But it's so useful. Conservation of energy is so useful for determining things. Basically, if you have a beginning and an end, if you can use conservation of energy, you should use that because it's so easy to use compared to like kinematics or forces or anything like that. You don't worry about directions. You can use conservation of energy for projectile motion problems. And what's cool is you can do it all together, or you can split into X and Y, like so many options. It's great. Anyway, things you need to remember is stuff. It's not going to be anything surprising. You need to remember that gravity is 9.8. Notice that I put positive here. That's because when we're working with stuff, remember we do not put negatives anywhere like in any of these equations. The only times negatives pop up, okay, I guess there's one exception to that. If you're below ground, if your initial position can be negative, that's fine. You'll plug that in. But in that case, that's something. We'll get to that when we get to that. But in general, pretty much everything goes in as a positive. And none of this should hopefully be surprising. Kinetic energy, we talked about the last week. Definition of work, you're going to see it like 5-6 times today. Work equals a change in kinetic energy. We're going to use that for some things. We're going to use that to help derive conservation potential, conservation of energy. Yeah, so anyway, there you go. All right, this is just definitions. Things you need to know what the word system means. You need to know what the word environment means. I've been kind of using these in the past week. This is just a slide with the definition of it. So a system is just like a zoomed in piece of it. So it's whatever part you care about. That could be you, that could be a car, that could be literally whatever you're trying to figure out. If you throw a ball, the ball is a system. The system is whatever you're trying to investigate. The environment is everything outside that. The environment is everything else. We always want to zoom in on something because if you look at everything, that's the whole universe. And the punchline of the whole universe is energy in the universe stays the same. Net force in the entire universe is 0. Universe, if you just look at the whole thing, on average, nothing happens. If you look at the entire universe. So we look at things inside the universe, because things inside the universe change. so on and so forth. Center of mass of the entire universe stays the same, whatever. So anyway, system is what you care about. Environment is everything around it. The reason we need to define this is because the system can gain or lose energy to what's around it. You know, if I slide this bottle on the desk, the bottle will slow down because it loses energy to the environment. The environment is the table, or literally everything around it. It is almost impossible for the system to be completely isolated from the environment. It's almost impossible not to lose or gain energy from stuff around it. We assume, we do all sorts of assumptions. We're like, we ignore air resistance, we ignore friction. But in the real world, it is almost impossible to not lose energy to the stuff around you. Friction is the most common case, heat, all that kind of stuff. So when you all get into engineering things, it is almost impossible to keep all your energy isolated. Lots of money goes into that. I mean, your house is a good example. Inside your house is a system. You cool the inside of your house. But as time goes on, the environment, literally outside your house, heats up the inside, and you have to keep putting more energy in to cool down your house. Lots of money goes into keeping the energy where you want it to be and keeping the external energy out, but it's impossible to fully isolate them. That's just an engineering thing. We will do plenty of examples, though, where we will assume that no energy is gained or lost, though. Anytime I've told you assume no air resistance or assume no friction, we were assuming nothing got lost to it. All right. Anywho, there you go. Things. Yeah, it's what we've been talking about. So this is just definitions, but it's important concepts. It's important that you know what the heck system and environment is. I mean, again, I remember being in your seat, and I remember these buzzwords getting said, and me having no sense of what the heck they were. But if you understand this, it gives you a better insight into what's going on. So, anyway, conceptual understanding. All right. This is just a poll of, have you seen the word gravitational potential energy before? This is very weird. When I move my mouse to the right side of the screen, I have no idea it doesn't happen on your, I had no idea. Sorry. You all probably were wondering why I freaked out about this. On my screen, it turns black, and I have no idea why. So if I turn my laptop around, you see what I mean? A random black thing comes up. I had no idea why this is happening, but you all, whatever, it doesn't affect y'all. I just need to, it's so weird. Oh, now it's gone. It's only weird. Anyway, if they're on the screen, they see it. They'll see my screen turning black randomly. Just have to avoid this corner. Anyway. All right, we'll go to a minute 10. Either you know it or you don't. Either this is something you've seen before. Gravitational potential energy, does it gain by going faster, going higher, sliding on horizontal ground, or warming it up? All right, in 5, 4, 3, 2, 1. All right, the whole point of this question is just to show you all, hey, you've seen this stuff before, very likely. And the answer is lifting it higher. Which, yay, a lot of us have seen potential energy before. What's going to be new in this class is now we're going to see where it comes from. So you all have actually probably, for those that said this, you've probably seen this before. Potential energy equals mgh. You might have seen that before. It's going to come up in a future slide. Don't worry, this isn't the one time it's going to show up. But we're going to derive it. Actually, you've already derived it a few times. It's the work done by gravity. All right. This is just a quick check before I show you all the equation. I just want to remind you all. If work equals this, integral of a to b f dx is the force parallel to the direction of motion or anti-parallel. This definition of work is something is missing from it. Something has been done in the background. So this is kind of, do you remember what is the equation for work? If there's an extra term that's not shown here. Basically, do you remember what that extra term is? Check your notes, check anything like that. The term that's not shown here tells you whether or not they're parallel or anti-parallel. Tells you the sign. See if y'all remember. Look in your notes. All right, we'll go for like 20 more seconds, 15 more seconds. It's fairly straightforward if you know it. And 5, 4, 3, 2, 1. All right. So what's missing here? What's missing is that work is technically defined as from A to B, F, D. I'm going to put DL here. And this is just to remind you of a couple of things. That's the one that I've been giving you. Remember, DL is just the direction you're going. That could be DX, that could be DY, that could be DZ, that could be DR. It's just, hey, which way are you going? And which way you're going, there's many variables, X, Y, Z, R. Those are kind of your choices. So, great. In this case, DX, DL becomes that, F is that. And so basically this is the term that was missing. It was kind of done in the background. Well, this one down here is positive. So what does that mean? If this is positive and not, there's no other random numbers chucked to it, that means in this case, theta is 0. And if theta is 0, that means they're the same direction. Or, up, they're both up, or they're both to the left, or they're both to the right. It doesn't matter. What does matter is that they're parallel. This is just a check. Do you remember the work equation? Do you remember that this cosine of angle is what determines the sine? If I instead had put work equal negative, if I had instead put the work equals negative from A to B, F dx, that'd be anti-parallel. The definition, whether it's positive or negative, comes from the angle. The reason I did this question, so in studio class today, on the next slide, this is going to show up, and I just didn't want us to forget that the cosine of the angle exists. It's really, really, really important because it tells you whether you're gaining energy, or losing energy. Really, really important. Whether or not you're gaining or losing makes a big difference. So, boom. All right, great. This is a derivation, so we're going to start with the definition of work. That's just what we show. And this is where I told you the cosine of the angle. We're going to say they're parallel to each other. So we're going to say we're moving in the direction of the force. Great. All right, fantastic. We replace F with MA because that's the definition of force. Woohoo. Now what? Well, if it's due to gravity, we replace A with G. And then we just integrate that, and we're going to find the equation for gravitational potential energy. We are deriving the equation. This is a derivation. I do not need you to know this derivation. Anytime I do a derivation up here, the purpose is just to show you that these don't come out of nowhere. Everything in this class builds and builds and builds. It's all connected. Every now and then, I'll teach you all something that says this is an observation of reality, and that's where this equation comes from. So when we get to the equation for the force due to gravity in like 2 weeks, between like planets, that one's derived from experiments. We'll get to that when we get to that. But these ones are all derived from work. Every single equation we do with energy is from work. Kinetic energy was from work. Potential energy is from work. Go ahead and do the integral. What is that integral? Integral from y initial to y final ng dy. We replace that dl with dy because that's the direction we're moving. Gravity only cares about whether you move up or down. M stands for mass. G stands for 9.8. dy is what we're integrating with respect to. Write this on your paper. Pull out the constants. Integrate. I highly recommend writing it out because half of us are wrong. Write this out. Pull out the constants. Integrate. All right, I'll give you all 30 more seconds. All right, in 5, 4, 3, 2, 1. All right, let's do this, y'all. That's just a math problem. There's no physics. I mean, the physics is setting up this integral. So work equals the integral. Great, that's the integral we're solving. It's equal to work. It's equal to the energy gained or lost. mg is a constant. Mass does not depend on where you're located. Gravity does not. Okay, gravity technically depends on where you're located. We're going to assume it's a constant for the sake of this. In a few weeks, we'll do this integral again where g is not a constant. But that's a future problem. The integral of dy is y. mgy. There you go. So it's mg y final minus mg y initial. Ta-da! You all derived potential energy. It happened. All right. There you go. You've just derived potential energy for yourself. MGH. It's right there. Yeah. That's a good. The y came from integrating. So right here, it's a good. I mean, if the good. Anytime you have a question, ask it because I can almost guarantee. If we look at the answers, a good amount of us miss this, and that's okay. Integral of dy is y. Yep, there's no y in there. So previously, when we did kinetic energy, when you all did kinetic energy, it was mv dv. And in that case, we had a v, and you integrated it, and you got the v squared over 2, and all that jazz. So that was for kinetic energy. Potential energy, it's just all constants. So there you go. Nice and straightforward. And again, this is what's new about this class, maybe versus something you took in high school stuff. Instead of just telling you potential energy is mgy, mgh. Now you see where it came from. Ta-da! Oh, and here's another important question. Before I go to the slide which says, hey, potential energy is mgh. How high up are you right now? Are you 0 meters high, 3 meters high, 6.31 times 10 to the 6 meters high, or 10 meters high? Yeah. Great question. You choose. All right. All right, take your best bet. You got 15 more seconds. In 5, 4, 3, 2, 1. All right, so thankfully one of your classmates helped you out. From what perspective, you get to decide. So every single answer here is right. Every single answer here is right. None of them are most correct. The most correct one is the one that makes your problem the easiest to solve. So we'll see that. Define zeros wherever your problem begins or ends so that one of your potential energies goes away. So when we do problems, we're going to choose a zero such that at some place we'll define potential energy as 0, and that just makes your life easier because it's less math. All of these are fine. You can define yourself as the reference. You can define the ground as the reference. You can define the center of the earth. That was the third option. That's the radius of the earth. It's all relative. So what does this mean? It means potential energy is all relative. We don't care about the value of potential energy. We care about the change in potential energy. Because it's all relative, we don't care about how much potential energy you have. We care about how much potential energy you have compared to another spot. That's what matters. If I move from here to here, do I gain potential energy or do I lose potential energy? That's what matters. Just like velocity. Velocity is relative. How fast you're going is all relative to something else. It's not about how fast you're going. It's about how fast you're going compared to something else. There's lots of terms that are relative. Velocity, position, and it turns out energy. Energy is all relative. So, there you go. There's the equation for it. And this value can take, depending on what you set as 0, will depend upon what your value is, and you just got to be consistent. You just have to be consistent that whatever you choose H is 0, whatever you define as 0, you may need to make sure that it stays 0 for the entire problem, and everything is measured with respect to that. So whatever you set as your reference, be consistent. And we're going to do some examples today, and we're going to see why like making smart choices on it just makes the math maybe a little bit easier, but it's fine if you choose something different. It's not going to kill you. Yeah. Oh, yeah. Totally valid. So I used U here, but if you want, if this is, you could do U or P or U, like all of these are the same thing. You're going to see me kind of go back and forth on them. I don't know. I tend to pick U just because it's a single letter and it's shorter. But if you want to use P, go for it. What is important is that you have little G's next to these, because we're going to learn that there's different types of potential energy. There's gravitational potential energy. There's spring potential energy. When you all get to physics 2, there's electric potential energy. The rule of thumb with potential energy, every single thing in the universe wants to get to lower potential energy. I don't care what type of potential energy it is. Everything wants to get to lower potential energy. You can use that to explain every single thing that happens in the universe. At least that's not a super complex system. It doesn't explain why people do bad things. But it does explain why things fall. It does explain how charges move. Everything moves to lower energy. It explains some quantum mechanics things, all that jazz. Yeah, it explains a lot in quantum mechanics, actually. Anyway, to that end, there you go. There's the equation. MGH, we derived it. It came from work. We did it last week when we were doing work stuff. We were using MGH. If you kind of look back, you'll start to see that. I had to go calculate the work done by gravity and a few problems, and it was MGH. Kind of, sort of. There's a little caveat to that. We'll see in the next slide. So, anyway, there you go. Everything is in joules. All energy. Potential energy is in joules. Work is in joules. Kinetic energy is in joules. Work done by friction, joules. Because it's all energy. It's all the same unit. It just looks different. All right. There you go. Woohoo. Try it out. What is the gravitational potential energy for a 10 kilogram object that's 5 meters above the ground? I do tell you, set the ground to 0. If I didn't tell you that, there'd be 2 answers here that are correct. But because I told you what 0 is, there is 1 right answer. On the test, if I ask a question like this, I will tell you what 0 is. If I say, what is the energy? If I ask, what's the change? That's a different story. Change is all relative. Oh, yeah. I need to go back and sign those all as correct. In case you forgot the equation. All right, we'll go to 140. You got 15 more seconds. All right, 5, 4, 3, 2, 1. All right, really straightforward problem. There's your mass. There's your height. So you just solve it. MGH. When you plug in G, you need to plug it in as a positive. Notice that none of these answers were negative. G, when you plug it in here, is a positive value. Why is that? If you all go back to our equation where we derived it, remember, y'all, that this is actually the magnitude. Remember when you do the work equation, it's all magnitude and things like that. So do not put a negative 9.8 here or you will get the wrong answer. If you're lucky, the two mistakes will cancel each other out, but get in good habits when we talk about energy. Now, your height can be negative. Where you end up can be negative. If I instead said for an object that is 5 meters below the ground, you would put it as a negative. All that is, that just means it's smaller than the energy below the ground is less than the energy at the ground. Negatives here don't tell you direction. It's just it's a smaller number. -5 is smaller than 0. -5 is smaller than -3. That's all the negatives mean in this case. All right, there you go. So that's just a little side. The answer is 490. It is joules. Newtons is for force. Joules is for energy. Yeah. Yeah. So if I gave the same exact problem, but I said 5 meters below ground, if I did this problem instead, then the potential energy would be mgh, and it would be 10 times 9.8 times -5. In which case, I would have -490. Negative here does not mean a direction. It literally just means it's a smaller number. So 490, if we subtracted these two, if we subtracted 490, if I said, hey, what's my change in potential? I go from 5 meters above ground to 5 meters below ground. If I wanted to find my change in potential, and I start 5 above, and I go 5 down, then it's going to be 490. Needs to be final minus initial. So it actually would be -490 minus 490. And my change in potential is going to be -980. The negatives just tell you they're just relative. They're just relative to each other. It doesn't tell you any direction or anything like that. It's literally just -5 is 2 less than -3. Or -5 is 5 less than 0. Yeah. So we'll see some examples. You'll see more examples with that. But all that to say, you can have a negative. It's all about position. If we look at our original equation for potential energy, it wasn't actually mgh. If we go back a few slides, it was mg y final minus mg y initial. And your y final can be a negative value. Where you're located can be negative. All right. That is a good point. I'll leave this here because it is important to know that you can have a negative energy. It doesn't mean, negative energy just means it's smaller than a positive energy. That's all it means. It's all relative. All right. Now we're going to derive the energy for a spring. We're going to start with the same work equation. So work equals the integral of f dx. Woohoo. We then do the substitution, the force due to a spring. So a spring, this is the equation for it. It was one of those things we talked about a while ago. So we make that substitution here. So F becomes Kx. Fantastic. Then you set your limits, xi, xf. It's just wherever you're located, how much you move. And you're going to integrate this. I will remind you all, K is a spring constant. It's how stiff a spring is. But the key word is a spring constant. Every spring has a set spring constant. If you buy a spring for any engineering applications, it will give you a number. It'll say 1 Newton per meter or 1,000 Newton per meter. The units for K are literally newtons per meter. It literally is how many newtons do you need to squish that or stretch that spring 1 meter. That's the definition of it. The spring constant can vary from 1 Newton per meter to thousands or tens of thousands of newtons per meter. It just depends how stiff it is. The spring in your all's pins, if you have a clicky pin, really, really small. The spring constant for your all's garage, in your garage, you have a spring that is there to hold things up. That's really strong. The springs for your all's car suspension, that's a really high spring constant. Anyway, that's just to give you a frame of reference for K. Do the integral. Integral from xi to xf of kx dx. i.e. derive the equation for the energy stored in the spring. Yeah. No, x is changing from xi to xf. All right, give you all like 15 more, 20 more seconds or so. All right, we'll close this out in 5, 4, 3, 2, 1. So this is just, again, a math problem. So work equals the integral from xi xf of kx dx. Pull out your constants. Integral of x dx equals k x squared over 2. And you just, plug the things in. So we'll pull the 1/2 out. Minus 1/2 kx initial squared. So there you go. We just derived the energy stored in a spring. Now, in this case, we do have a 0 point. Where is the energy 0? When it's not stretched at all. So if we set my initial at 0, i.e. it's not stretched at all, we make that second term go away. There it is. Woohoo. And you all just derived the energy stored in the spring. Also, I need to go back and give you all answers for these. I'm going to forget later, so please hold. Good job. I want to make certain I put all of them as the right answer because I always forget to do that. Boom, 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 boom. All right. All right, there you go. There's the energy stored in the spring, 1/2 kx squared. X is how much you stretch or squish your spring. Not all springs can be squished. Some springs are designed that they're like already all kind of coiled, like your garage spring. It's not actually possible to be squished. But we'll consider springs where you can squish or stretch it. It doesn't really matter though either way. Most springs can be squished or compressed, and it doesn't matter which way you go. We are assuming that you do not stretch the spring so much that you break the spring. So, if you've ever played with a slinky, if you stretch it too much, the metal undergoes, it's called plastic deformation, I believe, and at which point it does not snap back. So we're going to assume you don't break your spring. If you break your spring, obviously this equation doesn't work anymore. But assuming you stretch the spring within the elastic region, that's why it's called elastic potential energy. Elastic means it snaps back to its original. If you all ever take a materials properties class, you'll learn about plastic versus elastic deformation. Really, really interesting. But it basically comes down to materials. You can stretch to a certain point, and when you stretch past that, it doesn't snap back anymore. That's plastic deformation. Elastic deformation snaps back. You've experienced that in life. Lots of things, you fiddle around with it. At some point, it doesn't snap back. Again, slinky. If you ever broke a slinky, it underwent plastic deformation. All right, really straightforward, though. That's the energy stored in a spring. And that's the only 3 types of energy we care about in this class. Kinetic, potential due to gravity, and potential due to spring. So when we solve problems moving forward, and I say what energy is present, there's just 3 that you check. Is there gravitational potential energy? Is there spring potential energy? Or is there kinetic energy? It's a checklist of 3 things. That's it. Super, super straightforward. All right. Now this next slide is going to look a little weird, and we might be, but we're going to explain it. We're going to kind of go through why it's the case. It's nothing crazy. So the next slide says, work is the negative change in potential energy. And I'm going to derive this in air quotes. We already kind of derived it, but I'm going to show you the negative. If you all remember previously, work was the positive change in kinetic energy. That's something we derived last week. So what's weird here is this one's negative. And it's like, what's up with that? Why is this one negative and the other one was positive? Well, let's just derive that. So work equals the integral of F dl times cosine of theta. And let's look at gravity. We got two different ones we could look at. Gravity or a spring. In my opinion, gravity is nice and simple. So let's just do a problem with gravity and discover why it's negative. I think it's the easiest way to derive this. Let's pick something up. It really doesn't matter whether you pick it up or drop it. You get the same result. But let's say an object starts here and ends up here. Starts down low, it ends up high. Let's discover what happens. So, in that case, gravity is down, but I am moving up. So, what's that angle going to be then? 180. So, you get to see it, read it, like almost immediately you see it. So we're going to integrate. We are starting at a lower height. We are ending at a higher height. We start low, we end high in this example. And our force is mg. It's a positive. We're going to integrate with respect to y. But there's a negative sign. Ta-da! You all just derived it. Negative mg final minus mg y initial. Ta-da! There's the negative sign. If you do it the exact opposite, if you all instead lower the object, the cosine of the angle will be 0, but your y final will be 0, and your y final will be a positive. So if you do the exact opposite, you lower the problem, my final height is smaller than my initial height. And if you subtract 0 minus any number, you get a negative value. So you can check that out for yourself if you want. Yeah? Change in kinetic energy plus the change in potential equals 0. Yes. Assuming no other things are acting on it. Yeah. So that's the important caveat here. So we're going to use this. You kind of had to foreshadow it. So the question was, so change in kinetic energy plus change in potential energy is 0? Yes, assuming there's only kinetic energy and there's only potential energy in your problem. If we have someone pushing something or friction, we have to also include that. So, but this is a great segue. We're going to derive the conservation of energy equation. Remember, everything is derived from work. Everything is derived from that work equation. So to that end, let's, I'm going to make a new slide. So through the power of making a new slide, we're going to derive conservation of energy. Really, really straightforward. So let's just jot down those two things. We just said that work equals the change in kinetic energy and work equals the negative change in potential energy. If those are the only energies in your system, you don't have any work, whatever. All right, if A equals B and B equals C, then they equal each other. So these two things equal each other, right? Because they both equal W. If they both equal W, then they equal each other. So using these, we can say that the change in kinetic energy equals the negative change in potential energy. I just set them equal because they both equal W, so therefore they both equal each other. Great. Let's just kind of write this out. Kinetic energy final minus kinetic, and you know what? I'm going to flip things around. I'm going to do it the other way. It's just going to make the final result a little bit. It's going to keep our finals on the right. That's the only reason I did this. It doesn't matter what side they're on, but whatever. All right, so negative U final minus U initial equals kinetic final minus kinetic initial. I'll put E's to be consistent. KE initial, KE. Nope, that's backwards. Final minus initial, minus initial. Great. UF plus U initial equals KE final minus KE initial. And if you rearrange things and move all the finals to one side and all the initials to one side, ta-da, we derived conservation of energy. How exciting. Look at that. What I start with is what I end with. That's the punchline. The energy I start with equals the energy I end with. So again, in previous classes, if you took physics, they probably just told you this, but now we've derived it. That's the cool thing here. Every single thing comes from the work equation. That's why it's the first thing I taught you when it came to energy was the work equation, because everything comes from that, which is kind of cool. Just that one equation, work equals the integral of F dl cosine theta. To be honest, I need to look up where that equation came from because I'm not certain who defined that equation. Someone did. Probably. That guy did everything. I'm sure he did, but I'll double check. It might have been Joules. I mean, all the units are named after Joules, so because last guy named Joules, I don't know what his first name is, but it's significant, I'm sure. Anyway, great, woohoo! There you go. There's conservation of energy derived. Now, so I'm going to kind of jump a few slides, and then I'm going to jump back. Ta-da! There's the thing I just showed you all. It's the exact same thing. It's just typed up. And now I'm going to jump backwards. Okay, so this problem, based on my studio class, there's something I got to remind you all. Before we jump into the next problem, I want to show you all something. I want to point out something. And that is that according to this equation, I want to remind you all, change with respect to what is kind of the question. If you make a change really small, it turns into a derivative. That's what I want to remind you all. If you make a change really small, it turns into a derivative. So what does that mean? It means that work equals negative du. I'm going to put dl, I guess. I don't know. You could put like y or x or whatever variable you want. You can make this a derivative. A change is just another word for a derivative. If that change gets really small, it's a derivative. Get kind of used to that. If you all remember way back when we learned about, I told you all v equals change in x over change in time, i.e. dx dt. Okay? So that's just to remind you all that change, and in this case, it's with respect to location. That's the only way your potential energy changes, is if your location changes. All the equations I've given you, it's based on location. So to that end, we need to know this for us to solve this following problem. I needed to make that a bit more apparent than it is in this slide, because it wasn't apparent. All right, here's the problem. Find the magnitude of force corresponding to the following potential energy. Oh, and there's the answer. I'm going to get rid of the answer, not because it's a bad thing, but because I don't want you all to use the answer to work backwards to figure out how to get it. That's not a bad thing to do per se, but it might miss you thinking a bit more. All right, so what's given? We have an equation for potential energy. Step 2, what are we solving for? Force. All right. See if y'all can figure out how the heck to get from that to that. I'll give you a hint. Stuff we've been using over the last. It's from today. Literally from that slide I just showed you. That was one. And then it's from something from last week. Well, / we've been using it today a bunch of times. How do I get from potential to force? And I will tell you there's 2 steps involved. That's the other hint I'll give you. 2 steps involved. Two equations we're going to utilize. All right, so remember this one. It's definitely going to be, we're going to use that. That's the one step. It's the one I just showed you all. And I'm going to give you all some time. What's the next step? That just gives me work. That's not what I want. I need to do one more step. How do I go from work to force? What is the relationship between those two things? It's an equation we've used today twice. We've used it twice today. Work equals the integral of f dx. We will just assume that the angle, we'll just make theta 0 for the sake of simplicity. So we'll use just the, I'll leave it there. And at this point, all the physics is done. It's just a math problem. All right. So step 4, let's do it. I'm going to do it in the two pieces. So work equals negative du dx. Okay. So let's kind of reword that. Negative d dx of this equation. Negative a over x plus b over x squared. It's just a derivative with a negative sign in front. Go ahead and try it. Can you do that derivative? A is a constant. B is a constant. Nice simple derivative. Be careful with your negative signs. So you should get negative a over x squared. The negatives originally cancel, and you take the derivative, and it spits out another negative. Plus, the reason it's plus, same logic, 2b over x cubed. There's a negative that goes inside, but you take the derivative of 1 over x squared, and it spits out negative 2, and that gives you another, that cancels that out. Great, that's work. All right, so what? Now we're going to take this and put it here. So, move this little thing over so I have enough room. So negative a over x squared plus 2b over x cubed equals the integral of f dx. And you're probably like, what do I do here? It's a lot more simple than it seems. So this is effectively kind of like an algebra problem. If you're doing an algebra problem, what's the opposite of multiplication? Division. Opposite of addition. Subtraction. What's the opposite of an integral? Derivative. So you take the derivative of both sides and it gets rid of the derivative. It gets rid of the integral for you. So if we integrate, or if we take the derivative of both sides with respect to x, that's going to get rid of the integral, and the dx's will get rid of the dx's. Taking the derivative with respect to x gets rid of all that. And long story short, you get f equals the derivative of that again. So that's it. So this problem is really just a, one, it gets you kind of, hey, here are these equations, and it's some good calc practice. That's kind of the thing here. It's kind of using calculus in an algebra way. So F equals negative 2a over x cubed minus, that should be a positive, minus 6b over x to the fourth. Ta-da! And my b and my 6 look identical, and that's a problem. All right. Yeah.
So basically, force is the second derivative of
Yep. Yep. That's what it ends up being here. Yeah. So that's the end reveal here, is that force is the second derivative of potential energy, which is kind of cool. If you have potential energy as a function of something, if you take the second derivative of it, you'll get the force. Yeah.
Do you need a plus c for the integral?
That's a good question. In this case, we do not, because we're taking the derivative of it, which would get rid of that constant. Yeah, so if we had like evaluated that integral, you would have had a plus c, but if you took the derivative of that, the constant would have gone. No, you don't actually want a plus c because it disappears. Yeah. So yeah, long story short though, this does tell us, I think that's a great point that I'll actually put over here, that f equals the second derivative of u with respect to, whatever variable. That's kind of cool. Yeah.
I have a question.
Yeah.
You started to step 4, you said work equal to negative derivative of negative a over x plus b over x.
Yes.
Why did it make the derivative negative? Like, why is it negative derivative?
Because the relationship between work and potential energy, there's a negative there.
Oh, I see.
Yeah. That's a good question. Yeah. So it's because the relationship between work and potential energy has that negative. Yeah. All right, there you go, y'all. Good stuff. So this is more of a math problem than a physics problem, honestly. But it's a good one to get used to doing calculus within these contexts. Yeah. Yeah, that's a great question, and I'm fairly confident you're right on that. Yeah, thank you. Force should be the negative second derivative. Yep. So it's cool. If you have a function for potential energy, you can get the force from it. You don't need to know anything else. It's kind of nifty. All right. And vice versa. Okay. This slide is, I already told you all this. This is just a reminder. Energy is a made-up thing, but it stays the same. Yeah, there you go. All right. Okay. Conservation of energy. But I am actually going to write this second term a little bit differently. I want to give you all the general. So this is true if nothing else is happening. This is true, but I'm going to put it in a better way that's going to show up later. Energy initial plus any work done equals energy final. This is what you're going to be using pretty much always. If nothing else is doing, so when I say doing work, what's doing work? This would be like applied force or friction force. Anything other than gravity, springs, that's basically it. Any other force than gravity or springs gets chucked in that W. And the reason we put it on the left side is, remember, what is the definition of work is how much energy is added to a system or lost from a system. How much energy is added to a system or lost from a system. So if the work is 2 joules, my final energy is higher. Makes sense. If my work is negative 2 joules, my final energy is lower because I lost energy. So that's why work is on the left. Work is on the left because if you're gaining energy, my final energy is higher. If I'm losing energy, my final energy is lower. Just to, again, make that really clear. Let's say my initial energy is 3 joules. And let's say I do 2 joules of work to it. You do the math and you end up with more energy. Makes sense. Let's say instead, that's example 1. Let's say instead my initial energy is 3 joules. And let's say there's some friction and it does negative. It takes away energy. My final energy is 1 joule. Again, getting in the mindset, work is how much energy I gain or lose. Work is how much energy I gain or lose from the environment. Work is always like from something external. You can't do internal work. It's got to be something external. That's adding or taking away energy from the system. Okay. Cool. All right, this is a fun problem. I'm going to give you all a good amount of time to think through this. And I'm going to write stuff as you're solving it. If an object is dropped from a height of 10 meters, at what point is the final kinetic energy equal to the final potential energy? At what point is the final, at what, and let me even clarify this. At what height, and when I say a height, at what height, call the ground zero. At what height is the final kinetic energy equal to the final potential energy? I like this problem a lot. Assume no air resistance. Look at that. So assume no work done by friction. Assume no work done by air resistance. There is only gravity. No springs. So again, I'll tell you all, you're going to use this equation. And then you just consider there's no work done by friction, so we get rid of that. And then what energies are present? Is there any springs present? No. So we're just going to consider kinetic energy, and we're just going to consider potential energy. So kinetic energy initial plus potential energy initial equals kinetic energy final. That's the only energies present. Just to kind of write it out explicitly. And we can even simplify that a little bit. One of these terms goes to zero. One of these terms is zero. Let's figure out what's given in this problem. Y'all tell me. Height. So we're going to call that y initial equals 10 meters. Or you could say h initial if you want. Sure. H initial, Y initial, whatever. All right. What else? There's one more given in here. That's going to help us determine what term goes to zero. Yeah. The final height won't be, it's a good guess. The final height won't be zero because when the final height is zero, my potential energy will be zero, but my kinetic energy will not be. That's a good guess, though. There's actually two givens I'm going to jot down here. One's more of a relationship. Yeah? Why is the initial kinetic energy zero? You are correct. My initial velocity is zero. If my initial velocity is zero, so I'll remind you all kinetic energy is 1/2 mv squared. I'll remind you all potential energy is mgh. So long story short, that term goes away because V equals zero. All right. And the key, the last hint I'll give you all to solving this problem, this is so what are we finding? We're finding HF, but it's a very special HF. At what height is the final kinetic energy equal to the final potential energy? So you can kind of put this relationship, I'm going to put it as a given. You can kind of put it where you want. Potential energy final. This is not always true. This is not always true. In fact, it's pretty much never true. Like they're always generally different. But in this problem, that's a constraint. It says, at what height is this true? That's what we're determining. All right, so I'll move that equation from the top down to step 3, and then see if y'all can figure this out. At this point, I have given you everything you need. If you put all the puzzle pieces together, you'll be able to solve this. So I'll give you all a few more moments to try to figure this out. And then I'll show you all the magic. All right, we'll go for like 20. We'll go 30 more seconds. All right, give it your best guess. If you don't have an answer, we'll close this in 5, 4. Well, actually, you know what? I'll leave it open as I'm solving. I'll close it at some point while I'm solving it, but maybe you'll make some. I want to show you all what the magic step is. Take this and put it right here. So potential energy initial equals potential energy final. You can make a substitution. They're equal to each other, so I can replace KEF with PEF. I'm allowed. That's our constraint in this problem. It's a system of equations, but we kind of mess with it before we put in numbers. All right, so I'll give you all a few more seconds to then, discover whatever you're going to discover, but I think we're pretty good at this point. So we'll close this out in 5, 4, 3, 2, 2, 2. All right, pick some answer. We're looking pretty good. All right, and 1. All right. So to put all the puzzle pieces together, we end up with MGH initial equals 2 MGH final. If you're unsure where that just, you add them together. Oh, look, the M's cancel. Oh, look, the G's cancel. So when you solve for H final, it's just H initial divided by 2. And what's cool with this problem, it's really easy for me to make variations on this. At what height is the final kinetic energy equal to half the potential energy? And that just changes my little constraint here. And you can do stuff with it. At what height is my final kinetic energy equal to 1/3 the potential energy? And case in point, here's another variation on this. Oh, so the final answer is 5. 10 divided by 2 is 5. Which we look pretty good on. Oh, you're like, what's going on there? There we go. All right, let's do the same problem. But how fast is the object going? The answer is not as nice. I mean, if you look at all these answers, well, I guess you got 2.5. That's kind of a nice number. But now, I will say you do know the potential energy at this place. You actually know the height. So there's kind of 2 ways you can go about it. Try this one out. Same problem, except instead of saying at what height does this happen, I'm asking how fast is it going when this happens. And it's just playing around with the conservation of energy equation. That's all we're doing. We're just playing around with the conservation of energy equation. In fact, I will copy and paste everything from the last problem up to here. Look at that, because everything gets kept. My givens are the same. My equations are the same. You will need a calculator for this. I mean, I really don't recommend trying to. I guess you could kind of get close in your head if you wanted to, but it's not advised. And the key here, y'all, just to kind of keep things moving, we got the same relationship, but we don't care about height anymore. We care about getting kinetic energy, so make the swap there. We don't care about the final height, so get rid, put it in terms of velocity instead. All right, we'll go to like 340, so you got like 50 more seconds. All the clicker questions today. All right, we'll close this out in 10 more seconds. In 5, 4, 3, 2, 1. All right, so if y'all notice, I kind of put the next step there. Now we're just going to swap in kinetic energy final. So then mgh initial equals 1/2. Just to remind you all, that's just going to be double. So 2 times 1/2 mv final squared. Mass cancels. The 1/2 cancels with the 2. So long story short, V final equals the square root of GH. You plug in the numbers, and you get 9.9. If you all plug that in your calculator, you get the square root of 98. Square root of 98 is 9.89 stuff. All right, and if you all check your work, remember in the last problem, we said that the height final was 5. So if we put the pieces together, mgh final equals 1/2 mv final squared, you can actually check that that's true. If you actually plug in the numbers, again, mass cancels, you will find that g times 5, 9.8 times 5 equals 1/2 of 9.8 squared. And it all works. It is, if you have the time, it is always beneficial to check your work. That is something I encourage you all. I know the tests are tight and things like that, but in general in life, if you have time, check your work. I can almost guarantee you'll find some mistakes somewhere. And this is speaking from personal experience. All right, a few more things to kind of talk about next. So I'm not going to mention the class yet. All right. So this is what I've been kind of telling. Okay. 2 types of conservation of energy problems. There's ones where the system, where the environment adds energy, i.e. there's work done, and there's others where work is not done. That's it. So you got 2 situations. Either energy initial equals energy final, or energy initial plus some work done. That could be an applied force. That could be a friction force. Literally anything in the environment that's adding or taking away energy. So applied force, friction, air resistance, those are the 3 most common. So some work, 2 cases. Energy problems are really straightforward. All you do is ask yourself, what energy do I start with? Is there any work being done by friction or applied force? What energy do I end with? And then you plug and chug and you make your equation, you do the work. Next class, we'll spend a bunch of time on it. But before that, I'm going to prepare us for one problem. I will prepare us for the problem, and then we'll start the problem next class. So we'll finish a handful of minutes early today. But I'm going to prepare us for it, and then we'll kind of leave it there. And next class, we'll solve the 3 problems and actually start momentum. All right. So, yeah, here's a step. Is it even a conservation of energy problem? How do you decide that? If there's a beginning and an end, you should pretty much determine if you can use conservation of energy because it's so nice. Conservation energy is so much easier to use than like every other thing because it's all scalars. Every single projectile motion problem I gave you all from the last test could be done with conservation of energy. It's great. It's fantastic. For example, if I drop a ball, if I tell you I drop a ball from a height of 5 meters, how fast is it going when it hits right before it hits the ground? Really simple problem. mgh equals 1/2 mv squared. So easy to solve. Way easier than the kinematic equation. I mean, the kinematics isn't too bad either, but anywho. So there you go, friction, yada yada. All right, 2 more clicker questions, and this is going to prepare us. This is the problem we're going to solve. So I'm going to straight up tell you, we're going to consider what energy do I have. And so to prepare us for this problem, I'm going to ask you, what energy do I start with? Because that's how you do these problems. What energy do I start with? What energy do I end with? Set them equal to each other and do math. So here's my problem. I squish a spring. I have a ball squishing a spring. So this is my initial. Initial is always on the left. Final is always on the right. That's my initial. This is my final. In the picture to the right, what do I start with? I have it starting with it being squished. And then it ends with it at the highest point. It flies up into the air. So what kind of energy am I starting with in this problem? This is how you answer conservation of energy problems. What do I start with? What do I end with? All right, we'll go to 120. No math at this point, so just go with your gut. And we'll close this out in 5, 4, 3, 2, 1. Okay, so we go through our list. Is there elastic potential energy? Yes. Like, right off the bat, yes, there's elastic potential energy. I got a spring that's squished. If you have a spring that's squished, there's elastic potential energy. Now, in this problem, so this right, you could make the argument that if you decided to make the ground 0, if you decided to call this 0, then you could make the argument that there's gravitational potential energy. That's fine. I'll give the points for that. Yes, both those are fine. In the beginning, it's not moving. I guess if you really got crazy, you could say it's on Earth and the Earth is rotating and therefore, no, we're not going to I'm not going to stretch that far. No kinetic energy, and yes, it probably has some temperature to it, but we are not going to consider thermal energy in these problems because they're a nightmare to calculate. We're going to assume things stay the same temperature. All right? So to that end, I marked the second one as right, but for the sake of convenience, what we are going to do, remember, I told you I'll pick y as 0 as somewhere convenient. Let's call this 0, y'all. Let's say it starts at 0. Why is that convenient? Because then my potential energy is 0 and it's less math. So jumping to this problem, I start with only spring, no friction, no air resistance, so this term's going to go away. So spring energy equals, what energy do I end with? At the highest point, i.e. the final, what do I end with when it's at its highest point? This one, there's only one answered without, nope. All right, I'll close this out in 5 and 10 seconds. 5, 4, 3, 2, 1. All right. The answer is it's above ground. So this side is going to equal mg y final. And I'm going to warn you all, next class, y final is not going to be 5. And that's what I'm going to leave you all with and figure out why y final is not 5. Based on this picture, we'll finish it next class. We actually have to do the quadratic formula for this problem, as gross as that sounds. You'll see. Yeah, it's good for you. Yeah, it is. There's no avoiding it. All right, y'all have a good one.